Alright, so welcome back everyone. So in this video, we are going to solve a question on linked list again. So this question is basically the direct extension of the question that we solved in the previous video. So the previous video was about detecting the cycle in the linked list, right? So if the linked list contains the cycle, simply return true. If it doesn't, simply return false. But in this question, we have to actually find the starting point of the loop. Now, what is the starting point of the loop? I see you ask. It's simply the first node from the beginning which is part of the cycle. So in this linked list here, the 2 is the first node which is part of the cycle, right? So this is the thing that we have to return. The pointer to this node, that's what we have to return. Now here, the first node itself is the starting point of the loop because the cycle starts on the first node itself, right? So we have to return this. Now, if the list is null terminated or it doesn't contain any cycle, we simply have to return null as they are told here. Now again, the explanation here involves some use of this post variable or something like that. But when in doubt, simply see the function definition. You can simply see the function definition. It shows that we'll be given a head pointer, that is we'll get pointer to this first node, and we have to return a list node star. That is, we have to actually return a pointer to this starting point of the loop or cycle, if you will. And if it doesn't contain any cycle, simply return null, right? So that's the question. Now it is also a very famous question because it is direct a follow-up question from the previous question that we solved. And one more thing, I would assume that you know how to find a cycle in the linked list because we are going to pretty much do 80% the same job. So if you have watched the previous video, it's okay. Otherwise, I assume that you know how to find a cycle in a linked list. Okay. So think about how you will approach this question, and I'll roll the intro. Alright, so the video's flow is also going to be same as the previous one. First, I'm going to discuss the naive approach that a normal person will try to do, and then we'll discuss the optimized approach. Okay, so without any further ado, let's start. So the naive approach, as in case of the previous question also, it involves the use of a hash table. Okay, now why hash table? Again, I'll come to this in a bit. So what we do is in naive approach, we start from the first node and we go through each and every node and we check if that node is present in the hash table. If it is present in the hash table, then we have got our starting point of the loop. If it is not, then we'll simply insert in the hash table. Okay, I'll repeat myself again. I'll go through each and every node and I'll check. If it is not present in the hash table, then I'll include it. If it is present in the hash table, then we have simply got our starting point of the loop. Alright, let me just run the algorithm so things will get more clearer. So we'll start from 7. So I'll include it because it is not part of the hash table. Then I'll move to 3. Now 3 is not part of the hash table, so I'll include it. Now I'll move to 2. 2 is not part of hash table, so I'll include it. I'll move to -1. -1 is not part of hash table, so I'll include it. I'll go to 3. 3 is not part of hash table. Okay, I suppose you know why this thing works, right? Because its pointer is 100 and this pointer, let's say it's 500, then both nodes are not same, right? Because I am including the pointers here. I am not including the values in this hash table. Because if I include a value in the hash table, then it might give us incorrect results. Okay, so that's the very simple reason. This 3 is inserted here. So I'll move to this 0. And 0 is not present in the hash table, so I'll include it. Now it comes interesting part. I am reached again 2. Now here comes interesting thing. Now I will try to insert this 2, but 2 is already present. So when I say 2, I mean pointer, right? So let's just say if this was some 700. So when I try to again insert this 2 again in the hash table, then it is present. So that means we have got the starting point of the loop. Okay, so how did it work? We have got the starting point of the loop, but how did it work? So what happened is we actually started including every node, and eventually when we reach this tail, this is tail, right? So if you just think about it, when there is a cycle in the linked list, there is no terminology like tail, but we call this node as a tail because it is a node which connects the starting point of the loop. So that's the reason we call it tail. So the algorithm works like this way. We go through each and every node. We include every node in the hash table if it is not present. And when we reach tail, in the following iteration, we'll actually reach the starting point of the loop, right? This is the starting point of the loop. here. This is starting point of the loop. So after the following iteration, and when we check the tail, we'll basically reach the starting point of the loop. Now, when I try to insert 2, the 2 will be already present in the hash table. So I'll simply return this 2's pointer now. That's the way. Now, one case might happen when there is no cycle. So let's just say the example is something like this, like 3, 2, 1, and maybe this is null. So what I'll do here is I'll first insert 3, then I'll insert 2, then I'll insert 1, and I'll simply read the end of the list, right? I'll be here. So in that case, I'll simply return null because I've read the end of the list. So again, that is very simple. We go to each and every node, and first we check if it is present in the hash table. Then basically we have found the cycle. If it's not present, we include it. Now, eventually, what will happen is, as soon as we read the tail, in the following iteration, we will basically reach the starting point of the loop if there is cycle. Okay, so this might be making sense because it is very similar to the previous question only. Because in the previous question also, something like this already happened, right? When we read the tail, in the next iteration, we would come across a node which would be present in the hash table. So we can say, okay, the cycle is present. If it is not terminated, the cycle won't be present. Now, coming to time complexity, it is again very simple. We are just going through each and every node and keep on inserting it. So, and one more computation to just check if this 2 is present in hash table or not. It is again big O of n, really doesn't matter, big O of n plus 1 or n. And space, we are using this hash table, so that's why it's again big O of n. Very simple, because we are going to actually insert every node in the hash table before we reach the starting point of the loop. So that's the reason why the space complexity is also big O of n. Alright, so that's the time and space complexity. It's the algorithm. And now coming to the reason why we use hash table. Because at every iteration, what we are doing, we are simply inserting every node, right? And inserting and checking, right? We are first checking, and then if it is not present, then we are inserting it. So we are doing two things. First is lookup, or basically we want to check it if it is present or not. So we are doing a membership check, and then we are actually doing insertion. And a hash table is the only data structure which provides such functionality. So because due to this functionality, only the time complexity boils out order of n. Okay, if it was some other data structure, it might not be order of n because no other data structure provides this constant lookup and insert. So yeah, let's now discuss the C++ solution of this approach. So yeah, here is the C++ solution. Now you can actually implement in Java or Python. The data structure that will be used in Python will be set, and in Java it will be the hash it. But in C++, it is an unordered set. In the previous video, I actually used unordered map, right? But I realized there was no need of inserting the values, right? I just want the node pointers anyway. So here's my hash table. I've created it. Then I'll go through each and every node, and first I'll check it. If it is present in the hash table, if it is present, then simply return that pointer, right? If it is not, then simply insert in the hash table and move on. Okay. If I break out of the loop, then means the list was not terminated. That is, there was no cycle. And simply return the null pointer. And edge case is also handled here. What if the list is empty? Then the loop will break out anyway, and null pointer will be returned. So I hope you understand it. It was to be honest, almost similar, right? I just changed this line. If you remember the previous video, in the previous video, I just returned here true, and I returned false here, right? All right, then it's time to discuss the optimized solution to this problem. Now, we are going to basically extend upon the idea of void cycle detection that we used in the previous video. So the algorithm is like this. So these are the steps I have written for simplicity. So first step is to find the termination point. Now, what is this termination point? Now, this termination point is basically the node at which the hare and tortoise meet in the Floyd cycle detection algorithm. Now, if you don't remember the algorithm, here's how it works in a nutshell. So we have two pointers, tortoise and hare, and initially they both point to the first node, and we start moving the tortoise one step at a time, and the hare two step at a time. Okay. Now, since if there is a cycle, it is guaranteed that the hare will actually complete the cycle and eventually meet this tortoise. So this is in the nutshell how the cycle detection algorithm works. We move the tortoise by one and hare by two, and if there is a cycle, eventually the hare will catch up, right? So yeah, if you are still confused, then I would highly recommend that you watch the previous video. Okay, so first step is to find the termination point. So how will you find that? We'll simply run the Floyd cycle detection algorithm. So let's just run it. So I'll move the totals by 1, here by 2. Okay, totals by 1, here by 2, totals by 1, here by 1, 2, totals by 1, here by 1, 2. And this is the point where they met. Okay, so this is what I'll say is, this is my termination point. Okay, so I've just given it as a name as a termination point. You can name it anything, colliding point or anything. I just wanted to explain it. So that's why I named it termination point. Then what you do is, you actually create a pointer to the first node of the link. This is step 2. Make a temporary pointer point to the first node of the link. I'll come to the intuition in a bit, but just first bear with me how this algorithm works. I'll come to the intuition. I know you are waiting for that. Okay. So then I'll create a pointer to the first node. Alright. That's step 2. Then what we have to do is start moving this pointer. This pointer to the first node. And any of these two, but let's just keep things simple and move this slow pointer or maybe the tortoise. There's a pointer to the first node, the temporary pointer, and the tortoise one step at a time. Okay, so start moving them. This mode, let me move it by 1. Let me move it by 1. Let me move it by 1. And here, there is a time, there will be definitely meeting. Okay, there will be definitely meeting, and they will meet. Now, the point where they meet is the starting of the loop. And there's no coincidence why this happens. There's a proper reason. We are going to derive it. Okay, so let me repeat the algorithm again. First, find the termination point. That is, run the fluid cycle detection algorithm and find out the point where the hare and tortoise meet. And we found out it met at this. Okay. Then create a temporary pointer, which actually points the first node of the linked list. Okay, so this was the condition of the first step. Then make a temporary pointer which points the first node, and then start moving the temporary pointer and the tortoise by one step at a time. Okay, and eventually they will meet. Now at the node that they will meet will be the starting of the loop, and there is no coincidence. There's a reason why this thing happens. So that's the algorithm. Simply find the termination point, make a temporary point the first node, and start moving the tortoise in that temporary until they meet. And when they meet, we have found the starting of the loop. Now, but we need to prove why this works. So before we prove it, let's just find the time complexity. This will work. Okay, this will work in case of any linked list. There is no doubt about it. Is this algorithm that we will discuss. So let's just discuss the time complexity and then we'll see the intuition or the mathematical derivation how this thing works. So first, what we are doing is, first we are running the fluid cycle detection algorithm. So that we already discussed in the previous video. It's big O of n, and we are actually traveling some more nodes here, which are actually less than n. Let's just call them m nodes. Okay, let's just call this distance m. Maybe this 1, 2, it was 2 here, 2 in this case, right? 1 and 2, 1 or 2 or whatever you just see it. The leading factor is n here, right? So time complexity will be big O of n, right? Because the fluid cycle detection algorithm, we already discussed its time complexity. It was big O of n, and we just covered some more nodes which was less than n. So the time complexity is big O of n. Simple. And space complexity, we are not using any extra space, so it will be big O of 1. That's not. Okay, then let's prove why this algorithm works. Now, how can we be sure that this algorithm works? Now, we can be sure this algorithm works if I can prove somehow that the distance from this termination point to the starting point, so this yellow strip, is same as the distance from the first node to the starting point. By the way, this is a general form of a linked list I've taken. This dotted line represents there are some nodes in the middle if you want to think about it that way. Okay, so there are some nodes in the middle, this dotted line that represents. Think the distance in terms of length, because it will make easy for me to explain you. So when I say I talk in terms of length, what I mean is, if these are our nodes, then the distance between these two nodes is actually 2, because I will think in terms of length. Okay, so that's the assumption I'm making here. I'll think the distance in terms of length. Alright, so here I have taken some variables that represent some distances. Now this m, let's say this m is the distance from the first node to the starting point. Okay, and this k is the distance from the starting point to the termination point. Now it is still ambiguous to you. Consider this, something like this. Let's say they meet here. I don't know if they will actually meet here, but let's just assume if they meet here. So the distance from this first node to the starting point of the loop, this is what I'm talking about. This is 2 here in this case. And the distance from the starting point, this is the starting point, right? The termination point, the distance I'm talking about, this is what I'm talking about here. Now this k is this k. Okay. So this m is distance from the first node to the starting point here, in this case 2. And k is the distance from the starting point to the termination point. Okay, so that's that. And L is the cycle length. Okay, again you can think the cycle length. Here the cycle length is 1, 2, 3, 4. Cycle in terms of links only. So this L is 4. Alright, so these are my assumptions. I'm taking this n, k, and L. These are the variables. M is the distance from the first node to the starting point. K is the distance from the starting point to the termination. So let's find the distance traveled by the tortoise and the hare. Why I'm doing this, you'll understand in just a bit. So let's see what is the distance traveled by hare first. Okay, so what the hare will do is the hare will definitely cross this path, so it will travel m distance, and it has to travel that k part. Okay, but before it travels this k part, it might happen that it will just run few cycles. So what I'm saying is, let's just say this is my cycle again. So it will definitely cross the M part, okay, because it cannot meet the turtle if it doesn't reach the cycle, right? So here meets the turtle because of the cycle. If there is a no cycle, then it will reach the null termination part. The hare will first travel this M distance. There's no doubt about it. It has to do that if there is a cycle. And what can happen is, at the very worst case, it has to actually go through few cycles here. So if it goes through, it might go to one cycle. Let's just say that is 1, 2, 3, 4 distance. Okay, so it might have to, let's just say it might actually do some h cycles. This h is the number h into l. So what I'm saying is it has to travel this m distance, and it might go through some cycles. So if I reach here and go through some cycles, I'll be here only. Okay, so that's a very obvious thing. If I'm here, if I am traveling 4 nodes, if I'm traveling 4 links, there's 1, 2, 3, 4, that's one cycle, then I'll definitely be here only, right? 1, 2, 3, 4, I'll be back here only. And then I need to travel this k distance so that I can reach the termination. Make sense? Very simple. This hare travels m distance, then some cycles, and some cycles. So it will be here only if it travels that h into l distance, and then the k distance to reach the termination point. Very simple, right? Not how much I'm doing here. Okay. So let me write out for the tortoise dt. So it will also travel the m distance. Okay. It cannot meet the hare before going into the cycle. That's very obvious. And then it also has to travel the k distance. Now you can assume that it does some t cycles, but if you just think about it, it is not. It won't happen, right? It might not actually do the. Can at the very max do one cycle only, but let's just assume it does some t cycle. So what I'm saying is, it has to definitely cover this m distance here. So it has to definitely cover this m distance here. Then it can do some cycles, but if you think intuitively, it won't do more than one cycle or so, right? So let us assume assumption doesn't make sense. So when I'm at this point, if I do any number of cycles, that is these t cycles, I'll be here only. Okay, so it is clear. Why? Because if I'm here, if I do any number of cycles, that is any number of 4 distances, that is 1, 2, 3, if I can travel any number of times this 4 lengths, I'll be here only. I think you are getting it right. So this TL will make sure I'm again here only, and I have of course this travel this k distance to the termination point. So these are the distances traveled by the hare and tortoise. I hope it makes sense to you. What is the relation between them when they meet here? So of course, in the end, both hare and tortoise will be here, right? They will meet at the termination point. Now, what can you say about these two distances at that time? Okay, so what is the relation between the distances? Now, it is very obvious to see that the turtle is moving at a single speed. So you can say, and if turtle is moving at a v speed, then the hare is moving at a 2v speed. So what I'm saying is, hare is moving double the speed, right? So it's very obvious to see that. It's very obvious to see that this dh is actually 2 times dt. Why? Because it's of course starting with double the speed. We are moving it two nodes at a time, and the tortoise is moving one node at a time. So this is very obvious to see that. So let's just equate this thing then. What do we get by equating this? Alright, so after simplifying the equation, we got something like this, right? So you can say what I did here. It's just basic algebra, what I applied. I just equated this. I equated this all into this equation. So this is the main equation. And I found out something like this. M plus K will be L, this is important, L into H minus 2 into T. Uh, this part, if you see, what is this? This H is an integer, right? This is an integer. I was just considering as a number of cycles only. So this H minus 2 is what? This part is an integer, right? I just use this H and T to denote the number of cycles covered by hare and tortoise, if you will. This part is an integer, right? So important point here, okay? I'm making important point. Stick this in your mind. This M plus K, this M plus K is an integer multiple. It is an integer multiple of L. Okay, this is important. This is a very important point. This M plus K is an integer multiple of L. Now, why do you care? Let me make you understand in some. Let me make you understand here. So let's just say we have a cycle of let's just say this 4 nodes, okay, and I'm at some point here. Now, if I cover the cycle length here, L is 4, okay. Now, what if I cover 1L distance? What if I cover 1L distance? Where will be at? If I cover 1L distance, that is 4 distance, I will be at 1, 2, 3, 4, okay. I'll be at the same position. What if I cover 2L distance? If I cover 2L distance, then first 4 I'll be here, and next 4 I'll again be here. So if I cover 3L distance, then I'll again be here, right? First 4 I'll be here, second 4 also I'll be here, and third 4 I'll be here. So what it says? So if I am at some point in the cycle, listening to these words carefully because these are all what will create difference now. So when I am at a particular node in a cycle, and if I travel some integer into the cycle length, then I'll be at the same node. This is important and repeat it. When I am at a particular node in a cycle, I'm in the cycle, right? And if I travel distance equivalent to some integer multiple of the cycle, I'll be at the same node. Simple, very simple. We can simply observe it here. Okay. And what do we prove? And what do we prove? What did we just prove? We just proved that m plus k is an integer multiple of cycle length. Now, what does it mean? What does it mean? If I am at this termination point, this is some node in the cycle, right? What does it mean? If I am at this termination point, if I cover m plus k distance from here, if I cover m plus k distance from here, then I'll be at this point. Okay, very simple, because if we are in this, we are at some node in the cycle, and if I travel integer multiple of the cycle distance, then I'll be at the same point. And m plus k we have already proven it is the integer multiple of L, right? So if I am at this node termination point, and if I travel m plus k distance, I'll definitely be here. I'll be definitely be here, right? So what if I travel just m distance? Then I will be at a particular node from which if I travel k distance, I'll be at this node. It makes sense. So what I'm saying is, uh, from this node, if I travel 4 distance, then I'll be at this node, right? But what if I travel just 2 distance? 2 distance. So what if I travel 2 distance? Then I'll be at a node from which if I travel this remaining 2 distance, I'll be at the same node from where I started. So that's what I'm saying here. If from this point, termination point, I travel m plus k distance, which is an integer multiple of cycle length, I'll be at the same point, right? No doubt about it. But what if I travel just m distance? Here, just 2 distance. Then I'll be at a point from which if I travel k distance, I'll reach here. Make sense? If you don't get it, please rewind the video, you will definitely get it. So what is that point actually? From which if I travel k distance, I'll reach this point. That's simply the starting point of the loop, isn't it? That's simply the starting point of the loop. Right? If I travel some m distance from here, I'll be at a node from which if I travel k distance, I will be at the termination point. Now, what is that point from which if I travel k distance, I'll be the termination point? That is the starting point of the loop. Okay, so we have actually proven that if I travel m distance from here, I'll reach here. And to reach from the first node to this, we need m distance anyway. So what did we just prove? This distance is m. We just proved it. And this distance is also m. Make sense? So that's what we're looking for. We just proved that distance is also m. So now that we have proved this both the distances are same, it's very obvious that after m iteration they will definitely meet. And we have proved that when they will meet, that will be starting point of the loop. So I hope you understand the intuition. It is important you understand it. I didn't explain it too mathematically by equations. I tried to explain the intuitive way as possible and just use the simple equation. Alright, so it's time to discuss the C++ solution of this approach. Okay, it's a very easy and convertible to Python or Java only, so there's not a big deal about it. So here are my tortoise and hare, or slow and fast. That's what I'm naming them here. And this code up till this point is pretty much similar to the how we detect cycle, right? So this is the code where we move the slow by one step and the fast by two steps, or tortoise by one step, or hare by two steps. And if they catch up, then we have found the termination point. Okay. And this time around, we are doing something different, right? If we found the termination point, what we are doing is we are we have already initialized the temporary pointer. Okay, so we have initialized this entry before we start the loop. Now, as soon as the termination point is found, what we are doing is until that entry and our tortoise, the slowest tortoise, right? They are not equal. We move them by one, and we have already proven that they both will meet after m iterations. Okay, m being the distance from the first node to the starting point of the loop. Okay, we have already proven that thing, and eventually will return slow. Okay, they will be equal. And the edge cases are also handled here. If the list is empty, then this loop will be null. Or maybe if the list is null terminated, we will actually break out of this loop due to these two conditions. This fast equals to null or fast or next not equals to null. And you already know why we check both of these conditions. Because at every iteration, we are actually first accessing fast and fast of next. Okay, so that's the reason why we included both of these conditions. And if we didn't find any loop or the list is not terminated, we are going to return the null pointer. So yeah, that's it from this video. Everything, the source code and all annotations will be available in the description. You can feel free to check that out. Yeah, then thank you for watching. Leave a like if you get something out of this video.